chapter, simple harmonic motion. All right. So, if I remember right, maybe it's not even your book, but very often this chapter in books is called periodic motion. All right, we're going to be focusing on one specific type of periodic motion called simple harmonic motion. Okay, so periodic motion is basically any motion which repeats itself at with a regular period. Okay, simple harmonic motion is a little bit more specific than that. All right. So I'm going to read at you for a minute. I apologize. But so the idea is in any oscillation, since the motion repeats itself at regular intervals, you have to have a restoring force that brings it back to its original place, right? Otherwise, it would keep going in a straight line, and it wouldn't be motion repeating itself, right? All right. Simple harmonic motion is motion in which the restoring force, the force that brings your object back to its starting place, is proportional to the displacement from the center of its oscillations, okay? And we've seen this a gabillion times, right? F equals negative kx, right? So any type of spring is going to, well, I shouldn't say any type of spring. Any ideal spring is going to exhibit simple harmonic motion. Well, and we know that k is the spring constant, right? So does that vaguely ring a bell? Did you guys do any simple harmonic motion last year? Yeah. A little bit? Okay, cool. All right. Yeah, pendulums is one, springs, and those are basically the ones we're going to be talking about here. All right, so a couple quick definitions. So first of all, period. So remember, period, the symbol for period is a capital letter T. Just like when we were doing circular motion, period represents the time for the object to complete one full cycle, right? So in the case of circular motion, the period is the time it takes for your object to go in a circle once. Okay. In the case of simple harmonic motion or periodic motion, it's the time to complete one full cycle. So the time to go from there to there. Okay. Or if I bounce the spring, the time for the spring to go down and back. Okay. One complete cycle. All right. So the units for period is just going to be, technically it's just seconds. Okay. But there's sort of a seconds per cycle implied there. You don't have to say per cycle, though, because it's implied. So if I say this period is 5 seconds, it's understood that that means that's the time for one cycle. Cool? All right. And then frequency, you guys know what frequency is, right? Frequency is the number of cycles that you complete per unit time. So like the rotations per minute would be a frequency, right? So it's just the number of cycles you complete per second. So problems with either period or frequency, you guys? Okay, cool. All right, now, finally, angular frequency. All right, so in a minute, I'm going to bounce the spring up and down, right? So the spring's going to bounce up and down, up and down, up and down, right? So it would make sense to think of the number of cycles that it completes per second, right? It's going to go up and down however many times per second. All right. In terms of describing the motion, something that is often very helpful is to, instead of looking at just the regular frequency, and this might be new for you guys, instead of looking at just the regular frequency, we're often interested in what's called the angular frequency. All right, which is a little bit weird because your object is just oscillating up and down, right? It's not sort of turning through any angle. Okay? Even so, if we equate one cycle to 2 pi radians, and then convert, you can measure what's called angular frequency. And we can use the Greek letter omega to represent angular frequency. Please be careful. This is one of the times this year where the same symbol sometimes has 2 meanings. And it's really frustrating. But I've checked other textbooks, and it's not just our textbook. This seems to be the norm. Omega is angular frequency. Later on in this chapter, we're going to have problems that also have angular velocity, which is also omega. So F you, thank you very much, people who wrote the book, right? Okay, so I will make sure that I call attention to it and make it abundantly clear which omega we're talking about when that happens. All right? Yeah?
For angular velocity, do like omega sub v or something?
We're going to actually use capital omega for angular velocity for this chapter. That's what I've seen most books do. So it won't be an issue frequently, and when it is, I will call huge attention to it.
Then there'll be problems later after this.
Exactly.
Yeah. Right. Well, that's a unit though, right? That's ohms.
Yeah.
Not the quantity. So that's like W being work and watts. All right, so anyway, so angular frequency. So the angular frequency then is the number of radians completed per unit time. So our units are going to be radians per second. And then these two equations are not on your sheet. I apologize. I added these after the fact. So please make sure you understand the relationship between frequency and period. Oh, are they? Oh, cool. I see. Oh, all right. I'm dumb. I added them to the next slide thinking that I had forgotten, and I just apparently didn't look carefully enough. Okay, cool. All right, so everybody good with that? All right, so we can represent the position of an object in simple harmonic motion using a cosine function. Right? So this is our generic equation for the position of an object in simple harmonic motion. So bear with me for a minute. Some of you are groaning. This ends up not being, I don't think it's quite as bad as it looks like it's going to be. So hang tight for a minute. We're going to do an example and you'll see this and you'll be like, oh, I see why we're using trig functions. So hang tight for a minute, all right? So anyway, so here's the idea. So if you imagine this box oscillating back and forth, okay, and I'll show you a physical example of this in a minute. But so this, this spring is going to compress until it stops the box, and then it's going to, go back and forth like this, right? So it's going to oscillate between a position of positive xm and negative xm. The center rest position is called the position of 0. Right? So that m in xm stands for maximum. Okay, that's your maximum position. Okay? So your position at a given time is equal to your maximum position times this cosine mess, right? What's the biggest value that cosine can attain? 1. And what's the smallest it can attain? -1, right? So you're basically, this is a way of forcing your position to oscillate between positive x over m and negative x over m, right? Does that make sense? Okay? Ethan, you had a hand up, and I wasn't trying to ignore you. I just wanted to finish that one last.
Is that equation going to hold true?
Yes. Yeah, this is central to the chapter, and it's on the, the big list of AP equations. That equation is on there. Like, this is a big, big equation. Okay? Yes.
It's not the distance of how far it goes up and down, it's the distance it travels per time.
Hang tight on that for a second. Okay, because I'm going to do an example, and I think that'll help clarify what it is. Okay? So in math class, you guys learned how to graph trig functions like this, right? Right? And so there's the period, right, and the amplitude, right? So how did you guys, when you guys, and this is an honest question, I probably should have talked to one of the math teachers. How did you guys, when you guys write a trig function, let's do it over here. So you guys probably learned that you can write that, for example, y is equal to what? A sine x minus b. No constant in front of this?
You can sometimes.
Sometimes? Okay. But, so the idea is, this is your amplitude, right? And then this mess over here should somehow determine your period of oscillation, right? So for this, because there's no number in front of the x, your period, I think, is too high, right? Does that ring a bell? All right, so that's kind of where our angular frequency is going to come in, is it's taking into account that we're using sines and cosines, and so that 2 pi radians is sort of the inherent period, and it's about scaling the motion from 1 period to 2 pi radians. It's sort of like a conversion factor. Exactly. Okay. And I'm going to do a concrete example in a minute. Okay. So I think you'll be okay. Yeah. I am. I think. Yeah. Did I? Yeah. I'm 99% sure I am. I hope so, because I think I dropped an F-bomb earlier. All right. Or I alluded to one anyway. All right. Okay. So as I was saying, so your position is going to oscillate between your positive maximum position and your negative maximum position. Cool? All right. That's going to occur with an angular frequency of omega. Again, xm refers to your maximum displacement. It's often called amplitude, exactly as you would anticipate. Cool? All right. Now, this mess here, this omega t plus phi, that's the Greek letter phi if you're keeping score. If you prefer to say phi, I'm okay with that. So this mess, that omega t plus phi, is called the phase of motion. I think I saw that in one problem, but if you get to that problem and you're like, what the hell is the phase of motion? That's what it is. Okay? So, what the phi does is this. So pretend for a minute that the phi wasn't there. Pretend it was just cosine of omega t. Okay? What's the cosine of 0? 1, right? But the problem is our object might not have a position. It might not start at its maximum position at time 0, right? And similarly, as I wrote here, it might not start at a position of 0 at time 0. So phi is what's called the phase constant, also sometimes called the phase angle. As if it wasn't confusing enough, they give two names to the same thing. All right, and basically all it does is it shifts the cosine curve either to the left or to the right to make sure that you're at the right position at time 0. Again, I will show you all of this in a concrete example in a minute. Follow? Okay. You need to be super, super careful when you do that, okay? Just knowing, and it says it down here, so it says we're going to do an example. We can easily find the period of an oscillating object. So if we know XO, in other words, if we know the starting position and the direction of motion at that time, then we can derive the equation for position. Good? All right, so we're going to do an actual example, and I'm excited to see if this works. All right, so all right, so what I've got here, I just hooked up Logger Pro. I don't know if you guys can see, I've got this little motion sensor underneath my oscillating spring, okay? So I'm just going to bounce the thing up and down, and we'll collect data for it. Okay, notice what's being measured here. Position as a function of time. Okay, so position of 0 would be where the motion sensor is, right? Follow? All right, so I'm going to set this thing into motion. Hopefully it didn't get too badly moved last hour. We'll stay over the motion sensor, and let's go ahead and hit collect. We'll select data for... It's like a perfect sine curve, right? Okay, which brings me to a quick tangent. Sorry. I wish I hadn't just done that, I'm really sorry. All right, so let's make sure that you guys are all familiar with what the cosine of theta and the sine of theta graphs look like. This is, you need to understand this. All right? So cosine of 0 is 1, right? All right. Cosine of pi over 2 is 0. Cosine of pi is -1. 3 pi over 2 is back to 0. And then 2 pi gets us back up to 1, right? So cosine should look like this. So this is, we'll call it t, and this is cosine of t. Good? Now, this is an honest question because I, this being my first year, I kind of don't know what, how comfortable you guys are with math. But based on that, I think we're good. So what would, for example, what would cosine of t, let's do minus pi over 2. What would that do to this graph? It would shift it to the right pi over 2, right? Okay, so this graph would look like this. Cool? That's called a horizontal translation. All right? Be careful because the minus doesn't mean left, it means right. Excuse me, they're called a what? I've never heard it called that, but that doesn't mean that it's not.
Phase shift.
Is vertical?
Yeah.
I don't think I've ever heard it called that. Or if I have, I've since forgotten, which is also very possible. Okay, Mark. You're good. It's recorded, so your suspension. All right. I didn't say anything. All right. Okay, is everybody good with this? All right, and then cosine, or sine rather, begins at, its sine of 0 is 0, right? So if I do sine of t and t, we do pi over 2, pi, 3 pi over 2, and 2 pi, then you're going to get, right? So notice that this really, isn't this the same as, it's the same thing, isn't it? Okay? So sine and cosine are the same graphs, just shifted horizontally one way or the other, right? Okay? Now, so when you describe periodic motion, when you describe simple harmonic motion, really there's no reason why you couldn't use sine instead of cosine. Okay? But arbitrarily, the physics community has decided we're going to always use cosine for position. Okay? How are we when we get there? How are we going to find the velocity? We're going to use sine, but why? Because if you take a derivative, you're going to end up with either positive or negative sine or whatever it is, right? Okay? So by taking derivatives, we can very easily find our equation for position at a given time and, velocity at a given time and acceleration at a given time. Good? We lost anybody? Okay, cool. So we had this mess, and we want to come up with an expression for what that, what the position is as a function of time, right? Okay, so we need to know a couple things. First of all, we need to know how long one oscillation takes, all right? So remember, this horizontal axis here is time. So that's when it's at its highest position. Then it goes down and back up to its highest position. So if I find from here to here, that's going to give me my period in seconds, isn't it? Okay, so let's take a second and do that. So that point right there is at a let me double check and make sure I got this right. Yeah. Okay, so that's a time right there of, it looks like about 0.610 seconds. Good? And this one over here is a time of, let's just call it 2.24. At that point. So how do I find the period? Just subtract them, right? So let's see, our period is 2.24 minus 0.610, and it gives you 1.63 seconds. Cool. So that represents the time it takes for my thing to oscillate down and back up. Okay? So I feel like we should write that down. So we just figured out t is, what did I just say, 1.63 seconds. Oh, well, I ought to be able to use that to find the frequency. How do I find the frequency, guys? Just do 1 over that. So if I do that, it gives me 0.613 what? Hertz. Don't it? And then we can find our omega, our angular frequency. All right? So our angular frequency, you can either think of as 2 pi divided by t or 2 pi times f. It doesn't matter. Since this 1.63 wasn't rounded off, I'm going to use that. Doesn't really matter, though. So 2 pi divided by 1.63 gives me 3.85 approximately radians per second is my angular velocity. I'm sorry, angular frequency. Yeah, it's the same unit, right? Yeah. Okay, cool. All right, so now I know my omega. T is the variable. So now I need to find my maximum position and my phase shift, right? Phase angle. Sorry. Good? All right. So let's go back to our graph. All right. It occurs to me now that you guys probably, has everybody had a chance to sort of draw something resembling that, if not exactly that graph? Okay. All right. So let's do this. Let's take a second and figure out what our maximum position is and what our minimum position is. And basically rescale our position. Right? These problems are all set up so that our equilibrium point should actually be at x equals 0. You see what I mean? Yeah. Instead of having the motion sensor being a position of 0. All right. So I'm going to find the maximum position, the minimum position, and find the difference between the two. So this guy up here was a maximum position of, oh, why does that look different than what I remember it being before? Oh. Okay, well that's like 0.652, or sorry, 452. And then down here, we're at 226. 452, 226. 452, 226.
So that's the mark position.
What's up?
No table.
Why am I dumb? Oh, over here you mean?
Yeah.
Oh, I gotcha. Yeah, actually, if we're going to go that route, I guess, let's just do this. Let's just click on this, and then we'll click stats. Here we go. Max, 0.481. Min, 0.228. Cool? All right, so, I don't know. This is just going to be some sort of like side calculation. I don't even know if you need to write this down. You'll never have to do this again. So what do we get? 0.228 and 0.481. So x max is 0.2228. X min was, what did I say, 0.481? 481. Well, I clearly have those flip-flops then, right? Yep, I do. I'm not very smart.
I think it was only 2 twos.
It was 3. I said it wrong. Yeah. Damn it. Now I forgot the other number. 481. All right, so that means that 2 times our x max is going to be the difference between those two, right?
Yes.
Am I making sense? Do you guys understand what I'm doing here?
Yes. Yeah.
Everybody good? Francis, you okay? Or yeah, okay, sorry, I misread your facial expression there. No, let's see what we got. Let's see, 0.481 minus 0.2228. So you got 0.2582. Which means that our x max is half of that, right? So 0.1291. Okay, so now I know my x max. Did that make sense? All right, and the last thing we got to do is find our phase shift. And this is the part that's a little bit tricky, and I'll be honest, that's the part I'm a little apprehensive about. Okay, so I don't give you guys a full blank page here, I hope.
No.
Really? Ah, shoot, I'm sorry. Okay. All right, so far, here's what we've got. Oops. So far, here's what we've got. We've got our position at time t is equal to xm, which is 0.1291 meters, right? Times the cosine of omega, which is 3.85 radians per second, times t plus stupid 5. Sorry? Absolutely. All right, everybody good? All right, now I obviously haven't done the calculations here because the data we got was going to be dependent on, what we got here, right? So, What's up? You guys good? You sure? Okay. So as a quick comment, notice, I don't know if this is maybe what you were asking about, if you plug this period back into here, what should 1.63 times this give me? 2 pi, right? Right, because your period is, so that's where that angular frequency comes in. Okay, because it ensures that you complete one period in 2 pi radians. Cool? All right, so the last thing we need to do is we need to find that phi. So what we're going to do is we're going to pick one data point, a known data point, and solve for phi. Well, usually what you do is you use x naught. Okay, now unfortunately, because of the way this program works, you can't actually read what x naught is, so I'm going to ballpark it. Okay, but so that would just be, you know, whatever the coordinate is right there, right? Does that make sense? Okay. All right, so if I use the mouse, I think I can at least get an approximation for what it is. It looks like, oops. So it looks like it's at about 0.209. That can't possibly be right. It's almost 0.3, isn't it? Yeah, I know, but I was hoping that it would still let me. Ooh.
Stop staff. You have a confidential message for you. Please read it. Please open that up and read that again. A confidential message. Thank you.
Remind me to pause it in just 1 second. All right, so there's our x naught. All right, while I read this message, see if you can solve for phi. So the idea is, what this is telling us is at time 0, in other words, at time 0, my position is going to be point. Oh, that can't be right, damn it, because we got to scale it. Shoot. What, do you guys see what I just realized? What did I just realize? I changed the scale, right? By how much? Well, yeah, so let's see. So my max should be 0.129. Darn it, this didn't occur to me. So I need to do minus. What's wrong? Sorry?
There was like a shattering glass sound outside.
Oh, they opened a lock problem.
It sounds like that.
All right. So don't worry about how I got this. If you know how I got it, then great. But that's our starting position ought to be 0.278 minus 0.3591, right? Because it's got to be negative something, right?
Oh,
Yeah.
So I just shifted everything.
wait, 2 seconds.
So yeah, I'll go back to it. All right, so while I check the confidential email, figure out what this is, plug it in for your x naught, and see if you can solve for phi. Good? You got to be careful though, because remember cosine repeats itself. So there's one sort of trick there. All right?